Hello. So in this video, I wanted to talk a little bit about a number that's associated to a network called its redundancy. So I'm going to do this just with examples, and we'll see what it's referring to. So redundancy is a measure, and let's say exactly what the formula is. So we have the number of nodes in our graph is equal to, say, n. Okay. And then we can also say that we have the number of edges, um, and that's equal to, say, m. Okay. Then we can write down the redundancy to be, say, r, and r is equal to, oops, r is equal to m minus n minus 1. Okay. So let's take a look at what that number is in these two examples, and we'll see if we can understand what redundancy is really talking about. All right, so we're just going to count up these numbers for each of these graphs or each of these networks. So let me draw a little line here to divide these two examples. Okay, so in the first example, this is the one we looked at previously. We have nine nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. And we can go ahead and count those. So, or we can go ahead and record that and say n equals 9 here. Number of edges. We have 1, 2, 3, 4, 5, 6, 7, 8 edges. So we have m equaling 8. So in this case, we can go ahead and calculate r, our redundancy. And r is going to equal 8 minus 9 minus 1. 9 minus 1 is 8. The parentheses here do matter. So we have 8 minus 8, which is just 0. So we have 0 redundancy in this example. All right, let's go ahead and calculate this number on the other side. Let me move this up here. All right, so counting. 1, 2, 3, 4, 5, 6, 7, 8, 9 again. So here we have 9 nodes. And counting the edges of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 edges, so our m is going to equal 10. So if we want to calculate the redundancy on this graph or this network, we'll see that we have 10 minus 9 minus 1, which is 10 minus 8, which is 2. Okay, so let's see if we can understand. Of course, 2 is bigger than 0. And for a network, I'm going to make a statement here, and we'll see why it's true, I think, in time. For any network, the redundancy R is going to always be non-negative. It's never going to be a negative integer. It's always going to be greater than or equal to 0. So this example here is the smallest redundancy we can get. It's 0. And what does it mean, really? Well, you might have noticed that both of these are from prior videos, and the graph on the left is, in fact, a tree. And trees we described in many, many ways, but one of them was the n minus 1 edges property. And that stated that the number of edges, m, is equal to n minus 1. And if we have m equals n minus 1, then plugging in gives us the redundancy 0. So in fact, that property, the n minus 1 edges property, tells us that trees are the only networks that have redundancy 0. So let me say that. tree, and this can serve as another definition of a tree. A tree is a network with redundancy zero, or zero redundancy. And what is it, what is it measuring? What is this notion of redundancy measuring? Well, I want people to think of these networks as maybe laying pipes to get water to houses. So let's think of that particular example. So here we have 9 houses, and we want to link them all up to some pipes. And maybe our route will be some water tower or something. And so it's kind of pushing the water around. But maybe we can just think of them as just being interconnected this way. So then what you want to think is, what is the redundancy asking? Well, the redundancy is sort of a tolerance for if something goes wrong. So let's say a pipe bursts here, right? Then you need to send your repair crew and you need to fix this pipe. But when you do that, you have no redundancy. So what typically happens in a good, well-planned city is they will shut off the water for this pipe, and water will still flow over to these houses because there's additional routes for that water to take. The water can be pushed in other ways. So trees have zero redundancy. Everything's linked through some path, in fact, a unique path. But if something goes wrong, uh, you're in trouble, or at least some people have to go stay in a hotel for a few nights. On the other hand, if we look over here in this graph, we have redundancy of 2, which means that if one of these guys fails, and granted, this is not universal, so we have to choose something that's not a bridge here. But if, say, this guy fails, if this pipe fails in this plumbing system, well, then the water that was maybe going around, or maybe the water that was being pushed around this way will now be pushed around that way. There's another route that water can take to get to E. So in fact, you can have this pipe fail, and in fact, you could have another pipe fail. You have 2 different pipes that could fail in this network, and still have everything interconnected. So this redundancy is telling you sort of how many times you can have a failure of a link, and still have a connected network. Okay, so that's the idea of redundancy, and it's very useful in applications. But of course, it doesn't mean that 2 of any link can fail. As I was just pointing out a second ago, if this link fails, it's a bridge. And so that one's one you want to make sure doesn't fail, even though you have redundancy. So it's just that there can be 2 that fail, but the 2 may matter to the particular network. All right.